All right, ladies and gentlemen, we got colligative properties in this one. And these are properties that depend on the number of solute particles in the solution, right? They do not depend on the identity of the particles. Now, we care about the identity, right? But these properties arise from just having particles there, not necessarily what the particles are. Okay, and what are those properties? Well, the vapor pressure lowers, and we're going to talk about that. Then the freezing point goes down, the boiling point goes up, and then osmosis if the solvent undergoes osmosis, like water does. All right. So let's talk about this vapor pressure lowering. When a non-volatile solute, so what is a non-volatile solute? It's one that does not have an appreciable vapor pressure, right? Like sodium chloride, for example, or most of your ionic compounds are examples of non-volatile solutes where they're not going to evaporate from water. All right. So when you have a non-volatile solute that does not exert a significant vapor pressure, right, it is dissolved in a liquid. The vapor pressure exerted by the liquid decreases. That's Raoult's law. All right. So we have the observed vapor pressure is equal to the mole fraction of solvent. That's very important. This is the hard part right there, the solvent. A lot of times we do mole fraction. It's always mole fraction of solute. This one's a solvent. And then this is the vapor pressure of the pure solvent, right? And so hopefully that makes sense. If I have 100% water, then whatever water's vapor pressure is at that temperature will be what the observed vapor pressure should be. If I have 70% water, right, my mole fraction is 7/10 times whatever that observed vapor pressure is, I should have 70% of the observed vapor pressure. That kind of makes sense. Right, and the difference, if we look at here, the mole fraction of the solvent and the mole fraction of the solute, and then we can have, this is the vapor pressure of the pure solvent, whether it's water or whatever it is. All right, we can do a little math to show you what the difference would be. All right, and so you would have, we know that right here, 1 equals the mole fraction of solvent. Oh, I didn't switch colors on you. Still didn't do it. There it goes. Mole fraction of solvent and the mole fraction of solute. Hopefully that makes sense, right? That the mole fraction should add up to 1. So that means the pressure, all right, the pressure observed, P, all right, the pressure observed is going to be equal to 1 minus the mole fraction of solute times the vapor pressure of the pure solvent. All right, this equation is technically the same thing as this equation, right? We just rearranged the mole fraction and put it in. All right, I just wanted to cover this just in case your book does something to you. All right, so that means that, all right, we do expand this out. P equals your pure solvent minus your mole fraction times the pure solvent. Rearranging, right? So I have the two pressure differences, which is the change in pressure would equal, right, the mole fraction of solute times the pure vapor pressure. So that would be the difference in pressure. All right. So now, why does this happen? This occurs because the entropy of the solution increases. And that's a big factor that we got. All right. So now, if the solute is volatile and has vapor pressure, right? You're putting something like ethanol in water, or my example is going to be benzene and toluene. All right. Then the observed vapor pressure is the sum of the individual vapor pressures. Well, what do I mean? So I'm going to use benzene and toluene. All right. So that means the pressure of benzene would equal the mole fraction of benzene times the vapor pressure of pure benzene, as well as the mole fraction, the pressure of toluene equals the mole fraction of toluene times the pressure of pure toluene. All right. So that means my total pressure would be pressure of, I got toluene over there and benzene over here. You add them both up. All right, they both contribute. They're both vaporizing. So let's look at this. All right, I got a little chart here. What is benzene? That's a good question. Benzene is C6H6, so benzene H to C to C to C to C to C to C to C, and there are double bonds every other, and H is around. A lot of times you'll see it written like this. Toluene, we're going to add something different. Take the H off top and put a CH3 there. So you have double bonds. Oh, that was horrible. Let's try that again. I don't like that one. A lot of times I draw this one as that. All right, so those are two compounds. They have different vapor pressures. So let's look at this chart of Rayold's law. Now, if we have 0 benzene in the solution, we will have 0 vapor pressure of benzene, right? So on the axis here is pressure, the vapor pressure, and here is the mole fraction of benzene. So that means the mole fraction of toluene would be a 0 here and a 1.0 there, right? That's the mole fraction of toluene. But it's not, it's the opposite. So benzene looks something like that. So as we get the mole fraction going higher, right? You got half, 3/4, 100% benzene. It's going to be vapor pressure of benzene at whatever temperature we're at. Same thing happens with toluene. Now, toluene has a lower vapor pressure. All right? Something like that. Now, the observed would be the addition of the two up here. You add those two lines. This is the observed. So we have benzene and toluene. Right. And if we take this much and this much, it should be that much. Now, this is Rayold's law. It's really nice. The bad news, it works good here and good here. All right. If there's deviations from Rayold's law, right, which happen, okay, this does happen. If our intermolecular forces are similar and they like each other. All right, they like each other. The observed vapor pressure will be lower because they like each other. If the intermolecular forces are not alike and they don't like each other, the observed vapor pressure will be higher. All right, and that depends on, right? It depends. So it's not ideal, right? It's law. It's kind of like in this region, it's kind of like a guideline, and it's better towards dilute solutions. But that's what we have, right? That's Rayo's law. Okay, and this leads us to boiling point elevation. Just go here. Yep. All right, so let's do another axis. So that is going to be pressure, and that's going to be temperature. This is a phase diagram. And so in our phase diagram, let's just say we have water. And we're over accentuate it so we can see what happens here. All right. So then we have, let's just call this 0, let's call this 1 atmosphere. That line. And so we would have this temperature right here would be 0 degrees Celsius. And this temperature right here would be 100 degrees Celsius. All right. Well, let's redo that. Let's keep that in. We'll keep the normal boiling points right there. All right. Okay. What happens if, so the black is pure water. You got your critical point, you got your triple point. If we lower the vapor pressure, right, what happens is, all right, our line now comes down. Again, I'm over-exaggerating this in the chart. And we'll get another line. Try to mimic that line as much as I could. Okay. And so what happens is, this is the solution now. And if you look, we have these differences. And so down here, right, this is the new freeze, this is the melting point of the solution. And this is a delta T. And this is the boiling point of the solution, which is another delta T. So there's 2 delta T's, and they're different. All right. So again, if I labeled it, this is the solid, liquid, and gas or vapor. All right. And so what happens, because the boiling point elevation and freezing point depression, let me put that in there. When we put a solute into water, the freezing point goes down and the boiling point goes up. All right, and how do we calculate that? That's a great question. All right. Delta T, and so now this is freezing and this is boiling. So they have different delta T's, so they have different constants. All right, so delta T equals, and then this is for freezing, equals the freezing point constant, and the times is Kf, M, and I. Whereas boiling, delta TB, KB, M, I. Excuse me. All right, so what is this? So we got the freezing constant. Boiling constant. M is the molality. All right. And we got the freezing point that goes down and the boiling point that goes up. What is this I? The Van Hoff factor. With the Van Hoff factor, it depends on the particles, not compounds. All right. Think number of ions. Think number of ions. So, what do we mean by that? Molecules. All right. C6H12O11, etc., right? CO2, it doesn't matter what it is. I equals 1 because those are one particles in solution. They don't have multiple particles in solution. All right? Now, think of NaCl, right? Or sodium oxide, or aluminum sulfate. Right? Sodium chloride as 2, right? I is 2. Sodium oxide, I would be 3. I would have 5 particles for aluminum sulfate. Now note, so you know, measured I, or the measured Van Hoff factor, okay, versus the predicted or theoretical Van Hoff factor, right, are not always the same. So that doesn't necessarily mean they're going to be the same. Like, so the measured Van Hoff factor of sodium chloride might be 1.9, right? And so I'm not going to expect you to know measured ones. You're either going to calculate it or I'm going to tell you, right? Otherwise, I don't think that's right. But I can always, with a theoretical one, the predicted one, that's fair game because you should know how many what things break up into. All right, the next topic will be osmotic pressure. So with osmotic pressure, what is this? This is the pressure required to stop osmosis. All right. And what is this osmosis? The selective passage of solvent molecules through a porous membrane from a more dilute solution to a more concentrated one. This is vital in a lot of things we do, especially biology, medicine, right? Osmosis is amazing. It's a great property to have. Reverse osmosis, RO water, great. And so all this is fantastic. So what's it kind of look like here? So the original YouTube, all right, it should be perfectly symmetrical. I don't like that at all. I'm going to try that again, guys. Let's make a U. That'll work. No. Okay. That's close enough for us, our purposes. All right. And then right here, you get your semi-permeable membrane. So now I'm going to cheat and duplicate this. At the exact same. Perfect. All right, so we got our semi-permeable membrane. All right, so on the left side, I'm going to have just pure H2O. All right, and on the right side, I'm going to have, at the same level, we're going to have H2O, but we're also going to have solute in there. All right, and so what's going to happen, because, again, from entropy, is you're going to have a net migration of water that goes up with the solute on the right-hand side. Okay, so this is the before. This is the after. All right, and the difference here, right, what's going on is, oh, let me make that a little taller. Perfect. This is capital P in Greek for osmotic pressure. All right. This is why we don't drink seawater. Right. And so at this point on the right side, this is what we call isotonic, which means they have the same osmotic pressure. All right. And how is it calculated? Your osmotic pressure, pi, equals I, your molarity, the gas constant, and temperature. All right, so let's write these out. Osmotic pressure. Van 't Hoff. Molarity. Oh, I don't like that. Temperature. And R. What R do we use? Well, great question. 0.08206. And the units would be liters, atmospheres, moles, and Kelvin. All right, so we got to use those units so we kind of know what pi has to be in. Atmospheres, molarity, moles per liter. Temperature has to be in Kelvin. All right, so those are the colligative properties. Hopefully that works, and we'll see you next time, guys. Take care. Bye.